So this presentation is about deriving a shortcut formula for the population variance. It just reduces the amount of arithmetic that you have to do to calculate this by hand. And I'm just going to turn off the video here, go over to the document camera, and do just a little bit of algebra. So here's our definition of the population variance. Better start back over here. So the way you read this is the sum of the squares of xi minus mu, starting from I equals 1 and finishing at I equals n. You're taking all the x values for the individuals, x1 and x2 and x3, so forth. You're subtracting each individual's x value from the mean, see how far from average each person is. You square all those, add it up, and divide by how many people there were. So it's the mean squared deviation from the mean. Okay, so that's x1 minus mu squared plus x2 minus mu squared, and so forth, all the way up to xn minus mu, in parentheses, squared. We take that sum, divide it by n. Now you may remember from your algebra class, there was this thing called FOIL, where you take, when you're squaring a difference like that, you do, it's x1 minus mu times x1 minus mu. You use the distributive property twice. You end up with x1 squared minus 2 mu x1 plus mu squared. And then we go over to the next term here with the x2. And then we continue with all the terms until we get to the nth term, where capital N is the population size. And so we get that expression. Now with the associative and commutative properties, I can rearrange that a little bit. I'm going to get all these, the x1 squared and the x2 squared and the xn squared. I'm going to get all those together. And then I've got minus 2 mu x1 and minus 2 mu x2 and so forth. So I got those together. And then I've got all these mu squareds. You got mu squared plus mu squared plus mu squared. So this piece right here is just the sum of the squares of the x's. And over here it's, well, there's 2 mu x1 and 2 mu x2 and 2 mu xn. The 2 mu's in front of all of those can be factored out, can be brought out front using the distributive property, factoring out the common factor, 2 mu. And then over here with all those mu's, it's mu squared plus itself plus itself plus itself n times. Okay. So now I'm going to distribute. I'm going to multiply the 1 over n all the way across. Okay. So now let's look at this piece right here in the middle. I've drawn a circle around it. See what's happening there is I've added up all the xn's, all the xi's, added up all the x values and divided by how many there are. So you know what that is. That's just mu. So that term is 2 times mu, and then all this stuff is just mu again, 2 mu mu, or 2 mu squared. And then over here at the end, we have 1 over n times n mu squared. The 1 over n times n cancels out. And now I've just got minus 2 mu squareds plus 1 mu squared. So that's just minus mu squared. So to say this in words, we've got the mean of the squares, say the mean, the average of the x squareds, minus the square of the mean. Okay. So if you remember from an earlier video, the standard deviation is just the square root of the variance. So we use the lowercase Greek letter sigma for the population standard deviation. So sigma equals the square root of this thing we just worked out. And I don't know if it looks simpler than the original thing we started with, but there's a lot less arithmetic because in that original formula you had to do a subtraction for every single x value. If you got a big list of data, that's a lot of subtracting. Down here you only have to subtract once, and so it's just less work. And then for the sample standard deviation, so we had a definition for that, and we're using the letter S for that, for the sample standard deviation. And it was almost just like the population standard deviation. Except there's a dividing by n minus 1. And we don't know mu, we don't have access to the population, so we don't know the population mean. We'll use the sample mean instead. Without the square root, that sample variance is an unbiased estimator for the population variance. When you put the square root on there, it introduces bias again, but this is the best we can do. And you can do the algebra like just the same way I just did for the population variance. The thing is, it was nice the way the n canceled out in that last formula. N canceled out right there, and that's not going to happen here because it's an n and an n minus 1. They don't cancel anymore. Makes the formula a little messier. But I'm just going to write it down what you come to. Depending on which book you look at, you can get a common denominator, combine like terms. You can go one more step. All right, so there's a shortcut formula for your sample standard deviation, and I'll put in a separate video how you can use that for an example, and in fact you can do the examples from the workbook real quickly this way, because a lot of times down at the bottom of the table of data I'll show you the sum of the squares and I'll show you the sum of the x's, and so you can just put the two numbers right in there, and so you can do the calculation very fast without a lot of work. Okay, so that's all for this this video.